You know when you're watching a sci-fi movie and you see these astronauts just gently, peacefully floating through the majestic silence of the cosmos? Maybe they're sipping coffee out of silver pouches, gazing wistfully at the stars. Well, do me a favor and scrub that Hollywood illusion from your brain right now. Because the actual reality of leaving our planetary cradle, it is a brutally hostile, physically punishing gauntlet. So let's dive right into this explainer, where we're going to tear away all that cinematic romance and look at the absolute extremes the human body and our engineering must survive just to make a trip to our closest cosmic neighbors.
Welcome to today's explainer. We are breaking down what we call the astronaut's gauntlet. We're going to look strictly at the raw physics of it all, the invisible terrors hiding in the void of space, and the ultimate catch-22 of actually landing. We've come through the foundational science of interplanetary travel to give you a real, unfiltered breakdown of what it actually takes to survive out there. I promise you, by the end of this, you are never going to look at a rocket launch the same way again.
Act 1. The illusion of the float, the brutal reality of weightlessness.
Okay, so you might be surprised to learn that the actual thrust phase, the part where the engines are firing, makes up barely 1% of a space journey. The other 99%, you're literally just coasting. But to understand the physical toll of getting there, picture a basic spring scale. Here on Earth, before launch, everything is totally normal. You hang a 1 kilogram weight on the scale, and the dial reads exactly 1 kilogram. That's our baseline, right? That represents the normal, everyday gravitational pressure that our bones, our muscles, and our internal organs are perfectly evolved to handle.
Now boom, the rockets ignite. During that incredibly violent 1% of the journey, the acceleration is absolutely crushing. That 1 kilogram weight, it suddenly registers as 4 kilograms. For the astronauts strapped in, this means they are suddenly enduring 4 to 5 times their own body weight. It's so extreme that the only way a human body can actually withstand it without vital organs totally failing is by lying completely flat on these specialized, self-adjusting couches. It is essentially a manufactured nightmare of heavy gravity.
But then, the engines cut off. We enter that long coasting phase. And that scale? It drops to absolute zero. Now, this is the terrifying reality of weightlessness. It's not just about doing fun flips in the air. It means that all mutual physical pressure between objects completely vanishes. The pressure of your feet on the floor, the pressure of your organs naturally resting against each other, it's just gone. And our bodies simply are not designed to function long-term without that baseline resistance. If we don't address it, it leads to massive physiological complications.
Act 2. Spinning for artificial gravity. Fooling the human body.
So if absolute zero gravity physically degrades us on these long-haul journeys to places like Mars or Venus, what do? We have to trick biology by creating something that isn't actually there. The solution? Massive rotating cylindrical space stations. By spinning the station, we generate centrifugal force. This force basically pushes everything inside the cylinder outwards, right against the hull. If you spin it at just the right speed, the hull pushes back against the astronaut's feet with the exact same force as Earth's gravity. It's a brilliantly clever mechanical illusion to keep our bodies from wasting away in the void.
So the takeaway here is that future long-haul spacecraft aren't going to be these uniform single-gravity environments like you see in Star Trek. We're actually going to see a strict divide. You might have zero-gravity zones up in the central or upper sections, perfect for scientific experiments that need weightlessness. And then, paired with that, you'll have artificial gravity zones down in the spinning lower sections. That's where the crew will live, sleep, and exercise just to maintain their bone density and muscle mass.
Act 3. The hostile void. Invisible and physical threats in the vacuum.
Because outside the relative safety of the ship, space is not some empty, peaceful ocean. It's a lethal, high-speed shooting gallery. Think about the numbers 10 to 70. That is the estimated amount, in tons, of meteoric dust that strikes Earth's atmosphere every single day. We don't notice it down here because our thick atmosphere just burns it all up. But out in the vacuum of space, a ship traveling at immense speeds is flying completely unprotected through this invisible, relentless storm of cosmic debris.
And if you're wondering just how aggressive this dust actually is, back in 1953, the US ran this wild experiment. They sent these highly polished metal plates way up to an altitude of 140 kilometers. The total exposure to space, just 144 seconds. That's it. But when they brought those plates back down and checked them under a microscope, they found 66 microscopic impact craters. That averages out to almost 5 impacts per second per square meter. It's basically a microscopic sandblasting effect. Over a multi-year journey, that can completely chew up the outer hull of a ship, so yeah, space is incredibly abrasive.
But dust is just the small stuff, right? If you're traveling past the orbit of Mars, you face an immediate, ship-ending threat.
1,600. That's the approximate number of known massive asteroids just lurking in the asteroid belt between Mars and Jupiter. Hitting a speck of dust degrades your hull. Hitting even a tiny fraction of one of those 1,600 massive chunks of rock? Game over. The ship would literally need sophisticated radar arrays to detect them and automatically course correct well in advance because human reflexes just aren't fast enough.
And hey, if the space rocks don't catch you, the invisible killers just might. Astronauts face 3 major radiation threats. First, you've got ultraviolet rays from the sun, super intense, but thankfully fairly easily blocked by a standard metal hull. Second, cosmic rays. Now these are highly penetrating, intensely dangerous waves of radiation that slice right through normal metal. They demand heavy, extensive shielding. And third, ironically, it's an internal threat: nuclear radiation. Future deep space vessels are probably going to rely on atomic engines. That means the crew has to be protected by incredibly dense, specialized armor just to survive their own propulsion system. Because, nothing screams safe travels quite like armoring yourself against your own engine.
Act 4. The Perils of Landing. The ultimate interplanetary catch-22.
Okay, so you've survived the launch, the weightlessness, the sandblasting, and the radiation. You've arrived at your destination. But actually stopping? That is the most perilous part of the whole shebang. Depending on where you're going, you face 2 completely different, deeply terrifying landing scenarios: the atmospheric landing and the vacuum landing. One threatens to literally burn you alive, and the other threatens to leave you totally stranded without fuel.
First up, the furnace. If you are landing on a planet with a thick atmosphere, like Venus, or even coming back home to Earth, you use that air to slow down. But the friction generated by hitting dense air at cosmic speeds turns the spacecraft into a literal shooting star. The hull gets white hot. To survive this, the ship needs incredibly advanced, heat-resistant aerodynamic shielding. It is a violently turbulent descent, and it relies entirely on parachutes and the atmosphere itself to act as the brakes.
But what if you're landing on the Moon or Mercury, planets that have a vacuum, meaning absolutely no atmosphere at all, while you can't use parachutes and there's no air friction to slow you down? This is what we call the fuel trap. To stop, you literally have to turn your ship completely around and fire massive retro rockets against your direction of travel. And the paradox here is just staggering. To carry enough fuel to fire those massive retro rockets, you need a larger ship. But a larger ship is heavier. And a heavier ship requires, you guessed it, even more fuel to slow down. It's an absolute engineering nightmare of weight and mass.
So all of this really brings us to the ultimate question. We've seen the brutal reality here, from the brutal bone-crushing physics of acceleration to the bizarre degradation of weightlessness, the microscopic sandblasting of the void, and the terrifying catch-22 of finally trying to land. If space is this fundamentally violently hostile to human life and to our machines, are we truly prepared to pay the immense physical and engineering costs required to leave our planetary cradle? It's definitely something to think about the next time you look up at the night sky. Thanks so much for joining me for this explainer, and I'll see you next time.